Lol. A planet the color of a deep ocean sapphire is raining glass. Not metaphorically. Not in some poetic shorthand for violent weather. Silicate particles, forged in an atmosphere hot enough to vaporize rock, are swept sideways by winds faster than any storm ever recorded in our solar system. That is the reality of HD 189733b, and the strangeness of it deepens the more precisely we measure it. The planet sits 64.5 light-years away in the constellation Volpecula, close enough by cosmic standards that it has become one of the most closely studied worlds outside our solar system. Its mass is about 12% greater than Jupiter's. Its radius is proportionally larger. But neither of those numbers is what makes it remarkable. What makes HD 189733b remarkable is its orbit. It completes one full circuit around its host star every 2.2 days, traveling at roughly 152 kilometers per second. To put that in context, Earth moves around the Sun at about 30 kilometers per second. This planet moves 5 times faster, pressed into a tight gravitational embrace that keeps one face perpetually scorched and the other in permanent night. That orbital geometry is the source of everything strange about this world. When a planet orbits so close to its star, tidal forces lock its rotation, and the result is a planet divided against itself. A dayside that cannot shed its heat, and a nightside that never receives any. The temperature difference between those two hemispheres drives winds, and on HD 189733b, the models and the measurements agree that those winds reach somewhere in the range of 8,700 kilometers per hour, roughly 7 times the speed of sound on Earth. When astronomers first detected this planet in October 2005, using a transit observation, watching it cross the face of its star, and measuring the tiny dip in starlight, they expected a hot Jupiter. That category was already known. Large gas planets hugging their stars, too hot for chemistry as we understand habitability, interesting mostly as orbital puzzles. What they did not expect was that HD 189733b would turn out to be a natural laboratory precise enough to reveal not just that an atmosphere exists, but what it is made of, what it scatters, what it absorbs, and ultimately, what it rains. The blue color came first. In 2013, observations confirmed what earlier polarimetry work had suggested. This planet reflects blue light more strongly than red. The leading interpretation, supported by atmospheric models, is Rayleigh scattering, the same physical process that makes Earth's sky blue. But on HD 189733b, the scattering agents are not simply nitrogen and oxygen molecules. Spectral observations, including work done with the Spitzer Space Telescope, whose infrared data was published in the astrophysical journal Letters, and ground-based instruments including the UVES spectrograph on the Very Large Telescope, identified molecular signatures consistent with silicate particles suspended in the upper atmosphere. Specifically, the data are consistent with magnesium silicate, a mineral we know on Earth as a component of glass, with particle sizes estimated between 1/100th and 1/10th of a micrometer. This is where observation gives way to careful interpretation. The silicate condensate model is the leading explanation for the atmospheric scattering signal, but it is a model fitted to the data, not a direct sample. We cannot scoop a jar of HD 189733b's atmosphere and examine it in a laboratory. What we can do is measure the light that passes through the atmosphere during transit, compare the wavelength-dependent absorption and scattering to known molecular and particle signatures, and build the most consistent physical picture. That picture, supported by multiple instruments across multiple observing campaigns, points toward silicate particles aloft in a scorching upper atmosphere with temperatures estimated between roughly 1 to 340 and 1540 Kelvin. At those temperatures, silicates do not sit still. They are caught in winds that would shred any structure we have ever built. The glass rain that results is not falling gently. The particles are driven horizontally, sideways, in a perpetual high-velocity scour across the dayside. The phrase glass rain is accurate as a description of silicate condensate precipitation, but the mental image it invites, delicate crystalline drops falling through a quiet sky, is almost exactly wrong. The more precise picture is a sandblasting event operating at planetary scale, continuously, without pause, driven by a thermal engine that never switches off because the planet never rotates away from its star. There are observational limits worth being honest about. The polarimetric measurements that initially contributed to the blue color determination have been disputed. Two separate teams using more sensitive polarimeters placed upper limits on the polarimetric signal that challenged the earlier result, which means the color confirmation that ultimately stood came from independent photometric methods rather than polarimetry alone. The silicate condensate interpretation itself rests on spectral modeling that involves assumptions about particle size distribution, atmospheric pressure profiles, and the vertical mixing of gases. Sodium has been detected in the atmosphere using high-resolution spectroscopy, and carbon dioxide was confirmed, a first for any exoplanet atmosphere at the time. But the full compositional picture remains a work in progress. Different models can fit portions of the data with somewhat different chemistries. The best current explanation, ranked by how well it accounts for the full body of evidence, is this. HD 189733b is a tidally locked hot Jupiter whose extreme proximity to its star drives a thermodynamic engine of enormous power. That engine suspends silicate particles in the upper atmosphere, produces the observed blue scattering signature, and drives supersonic winds that carry those particles around the planet in a continuous high-energy circulation. The glass rain is the visible signature of a planet where the chemistry of rock and the physics of extreme heat have combined into a permanent atmospheric state that has no parallel in our solar system. What would change or confirm this picture? Transmission spectroscopy at higher resolution, particularly in infrared wavelengths where silicate features are more distinct, could sharpen the compositional identification. Phase curve observations, tracking how the planet's brightness changes as it orbits and different hemispheres come into view, could test the wind speed models more precisely. Space telescopes with greater infrared sensitivity than Spitzer could push the atmospheric characterization deeper into the pressure structure, potentially distinguishing between competing condensate chemistries. Each of those observations could narrow the uncertainty or, in principle, reveal that the silicate model needs revision. HD 189733b was the first exoplanet to have a thermal map constructed, the first to have its overall color determined, the first to have carbon dioxide confirmed in its atmosphere. It sits only 64.5 light-years away, which in the context of a galaxy 100,000 light-years across is an immediate neighbor. And yet we have never visited it, never will within any foreseeable human timescale, and know everything we know about it from starlight. From the way light dims when the planet transits, the way it dims differently again when the planet disappears behind the star, and the way the spectrum of that light shifts at different wavelengths. The deeper consequence of HD 189733b is what it demonstrates about the range of planetary conditions that physics permits. We built our intuitions about weather, atmosphere, and climate from one world. This planet, a blue giant racing around its star in 2 days, raining glass at supersonic speeds across a surface hot enough to melt aluminum, exists within the same physical laws. The same Rayleigh scattering that turns Earth's sky blue gives this world its color. The same silicate minerals that make up much of Earth's crust are suspended as condensate particles in its upper atmosphere. The physics is shared. The outcomes are almost unrecognizable from each other. That is the genuinely strange thing. Not that the universe contains extreme worlds. We expected that. But that extreme worlds and temperate ones are written in the same equations, shaped by the same forces, differentiated only by distance from a star, by mass, by the accident of where a planet formed and how its orbit evolved. HD 189733b is a reminder that the range of what is physically possible far exceeds the narrow slice of it that life, as we know it, requires. The glass rain falls on a world that follows all the same rules. It just started from a very different place.